Welcome to all of you. I, Dr. Pulok Sahu, working in the Department of Mathematics, University of Kolkata, West Bengal, India. Today we discuss paper 7, complex analysis. So first we give some historical background of complex numbers. The numbers of the form a plus b root over minus 1, where a and b are real numbers, what we call complex numbers, which appeared as early as in the 16th century. Cardan first worked with complex number in solution of quadratic and cubic equations. In the 18th century, functions involving complex numbers were found by Euler to yield solution to the differential equation. However, complex number enjoyed poor reputation and generally not considered as a legitimate number until the middle of 19th century. Descartes rejected the complex roots of an equation and coined the term as imaginary for such roots. Euler also felt that complex number exist purely in the imagination, and he considered complex roots of an equation is useful in showing that the equation has ultimately no root. The wider acceptance of complex number is due largely in the geometrical representation of complex numbers, which was fully developed by Gauss. He realized that there was some dark mystery in the complex number. The complex number was established by Gauss, but the formal definition was given by his contemporary William Hamilton. Now we go to chapter 1, that is complex number, and we will discuss module 1, that is basic idea of complex numbers. So first we give some introduction. There is no real number x which satisfies the equation x square plus 1 equal to 0. To permit solutions of this and similar kind of equations, the set of complex numbers was introduced. The term complex number was introduced by C. F. Gauss, a German mathematician. Later, the subject was enriched by the original work of A. L. Cauchy, B. Riemann, K. Weierstrass, Liouville and many others. Let us denote by R the set of all real numbers. Consider R2 the set of all order pair of real numbers x, y defined by R square equal to the set of elements x, y, where x belongs to R and y belongs to R. Here order means x, y and y x are distinct unless x equal to y. Now we give definition of complex number. A complex number is defined as an order pair x, y of real numbers x and y satisfying the following rules. Number 1, order pair x, y plus order pair z w is equal to order pair x plus z y plus w. Number 2, order pair xy into order pair zw is equal to order pair xz minus yw xw plus yz. Number 3, order pair xy equal to order pair zw if and only if x is equal to z and y is equal to w. And number 4, m into order pair xy is equal to order pair mx my, where m is any scalar number. We denote by I the order pair 0 1 and the real number x by the order pair x 0. From the above definition of complex numbers, we see that order pair xy is equal to order pair x 0 plus order pair 0 y, and this is equal to x into order pair 1 0 plus y into order pair 0 1, and that is equal to x plus I y. Also we see that I square, that is equal to order pair 0 1 into order pair 0 1, and that is equal to order pair minus 1 0, and this we obtain by multiplication rule, and this is equal to minus 1. Now we discuss fundamental operations of complex numbers. Suppose that z1 equal to x1 plus I y1 and z2 equal to x2 plus I y2 be any two complex numbers. Then we define the operations of addition, subtraction, multiplication and division by number 1, addition x1 plus I y1 plus x2 plus I y2 equal to x1 plus x2 plus I into y1 plus y2. Subtraction x1 plus I y1 minus x2 plus I y2 is equal to x1 minus x2 plus I into y1 minus y2. Then multiplication x1 plus I y1 into x2 plus I y2 is equal to x1 x2 minus y1 y2 plus I into x1 y2 plus x2 y1. And number 4, division x1 plus I y1 by x2 plus I y2 equal to, we can write x1 plus I y1 into x2 minus I y2 by x2 plus I y2 into x2 minus I y2, that is equal to x1 x2 plus y1 y2 by x2 square plus y2 square plus I into x2 y1 minus x1 y2 by x2 square plus y2 square, provided that z2 is not equal to 0. From the above definition, it is obvious that the set of all complex numbers forms a field with respect to addition and multiplication. Now we define complex plane or Argand plane. Every complex number can be represented geometrically as a point in the xy plane. Now we shall call this plane as complex plane or Argand plane. Introducing a rectangular Cartesian coordinate system in the plane, we can identify the complex number z equal to x plus I y with the point P as coordinate x y. Obviously, the set of all real numbers x comma 0 corresponds to the x axis, and we call this as real axis, and the set of all purely imaginary numbers, that is order pair 0 y, corresponds to the y axis, and we call this as imaginary axis, while the set of all imaginary numbers corresponds to all points which do not lie on the real axis. The origin identifies the complex number 0, that is equal to 0 plus I into 0. The complex plane is generally denoted by C and is often called the Z plane. For any complex number z equal to x plus I y, we call x as the real part and y as the imaginary part. The non-negative number mod z, called modulus or absolute value of z, is the distance of the complex number z from the origin, and hence modulus z is equal to root over x square plus y square. And see this figure, here z is x y. So, modulus z is the distance of z from the origin. The distance between 2 points z1 equal to x1 plus I y1 and z2 equal to x2 plus I y2 in the complex plane is given by modulus z1 minus z2, and that is equal to root over x1 minus x2 whole square plus y1 minus y2 whole square. We shall frequently use the simple inequalities. Number 1, x is less or equal to modulus of x, and this is less or equal to root over x square plus y square, and this implies real z less or equal to modulus of real z is less or equal to modulus of z. And number 2, y less or equal to mod y less or equal to root over x square plus y square, and this shows that imaginary z less or equal to modulus imaginary z less or equal to modulus z. Till now we give the definition of complex numbers, and then we discuss fundamental operations of complex numbers. Then we introduce complex plane or Argand plane, where a complex number can be represented, and then we discuss the distance of a complex number from origin and the distance between any 2 points. Now we will discuss conjugate of a complex number, polar form of a complex number, and roots of complex numbers, and lastly we will give some examples. So, now we define conjugate of a complex number. If z equal to x plus I y is any complex number, then its complex conjugate denoted by z bar is z bar equal to x minus I y, that is z bar equal to order pair x minus y. Obviously, z bar is the mirror image of the complex point z into real axis. it is obvious that z is equal to z bar if and only if z is purely a real number. Also, the conjugate of z bar is equal to z. Now, the following are the easy consequence from the above definition. Number 1, conjugate of z plus w is equal to conjugate of z plus conjugate of w, where z and w are any two complex numbers. Number 2, conjugate of z minus w is equal to conjugate of z minus conjugate of w. Number 3, conjugate of z into w is equal to conjugate of z and conjugate of w. Number 4, z plus z bar, this equal to twice real z. Number 5, z minus z bar is equal to twice I into imaginary z. Number 6, z z bar is real and positive unless z equal to 0. Number 7, conjugate of z by w is equal to conjugate of z by conjugate of w. And number 8, modulus of conjugate of z is equal to modulus of z. Now, we discuss polar form of a complex number. Let r and theta denote the polar coordinates of a point z equal to order pair x y. For z not equal to 0, we consider x equal to r cos theta and y equal to r sin theta. Then obviously z can be written as z equal to r cos theta plus I sin theta, and this is called the polar form of a complex number. Here r is equal to modulus z and is equal to root over x square plus y square, a unique positive real number is called the modulus or absolute value of z, and theta is equal to tan inverse y by x and is called the amplitude or argument of the complex number z and is denoted by small arc z, and for this see figure 1.2. So, here p is a complex number, z equal to x plus I y, and r is the modulus and theta is called the argument of z, that is the p. Given a non-zero complex number z, its argument does not have a unique value. There are infinite values differing by multiples of 2 pi. For many purposes, it is useful to restrict the allowed range for the polar angle theta so as to get a unique value of theta for a given z. If the value of theta, that is of argument z, is restricted to lie in the range from minus pi less than theta less or equal to pi, we obtain the principal value of small arc z, and which will be denoted by capital arc z. That is, capital arc z is equal to theta, where theta varies from minus pi to plus pi and theta may be equal to pi. It must be noted that small arc z is not defined for z equal to 0. Now, we summarize few properties of modulus and arguments. Let R1, R2 and R3 be the moduli of the complex numbers z1, z2 and z3 respectively. Also we suppose that theta 1, theta 2 and theta 3 denote the argument of the complex numbers z 1, z 2 and z 3 respectively. Then number 1, if z 3 equal to z 1 into z 2, then R 3 equal to R 1 into R 2 and theta 3 equal to theta 1 plus theta 2. Number 2, if z 3 equal to z 1 by z 2, then R 3 will be equal to R 1 by R 2 and theta 3 will be theta 1 minus theta 2, provided that R 2 not equal to 0. Number 3, if z 2 equal to 1 by z 1, then R 2 will be 1 by R 1 and theta 2 will be negative theta 1, that is minus theta 1. In this case also, provided R 1 not equal to 0. If z 2 equal to z 1 to the power n, then R 2 equal to R 1 to the power n and theta 2 will be n into theta 1. Now we discuss roots of a complex number. A number w is called an nth root of a complex number z if w to the power n equal to z, and we write this as w equal to z to the power 1 by n. If n is any positive integer, then we can write z to the power 1 by n is equal to r into cos theta plus I sin theta whole 1 by n, and that is equal to r to the power 1 by n cos 2k pi plus theta by n plus I sin 2k pi plus theta by n, where k equal to 0, 1, 2 up to n minus 1. From this it follows that the equation w n equal to z has n distinct values provided z not equal to 0. Now we give some example. Example 1, for any two complex numbers z 1 and z 2, we have modulus z 1 plus z 2 is always less or equal to modulus z 1 plus modulus z 2. We have modulus z 1 plus z 2 square, that is equal to z 1 plus z 2 into conjugate of z 1 plus z 2, since we know that mod z square equal to z into z bar. So, this equal to z 1 plus z 2 into z 1 bar plus z 2 bar. Then just we multiply and get z 1 bar plus z 1 z 2 bar plus z 2 z 1 bar plus z 2 z 2 bar, and that is equal to mod z 1 square plus twice real z 1 z 2 bar plus mod z 2 square, and that is less or equal to mod z 1 square plus twice modulus z 1 z 2 bar plus modulus z 2 square, because we know real z less or equal to mod z, and so this equal to mod z 1 square plus twice mod z 1 mod z 2 plus mod z 2 square, and this is equal to modulus z 1 plus modulus z 2 square. Here we use the relation that mod z 2 bar is equal to mod z 2. So, now taking the non-negative square roots of both sides, we get our required result. So, please be noted, the above inequality is known as the triangle inequality. The geometrical meaning of the triangle inequality is that the length of one side of a triangle is less than or equal to the sum of the lengths of the other two sides. And another one, the triangle inequality can be generalized immediately to the case of n complex numbers using mathematical induction, and which can be written as modulus z 1 plus z 2 plus up to z n is less or equal to modulus Z1 plus modulus Z2 plus up to modulus Zn. Now, example 2, for any two complex numbers Z1 and Z2, we have modulus Z1 minus modulus Z2 is less or equal to modulus Z1 minus Z2 is less or equal to modulus Z1 plus modulus Z2, and number 2, modulus Z1 minus modulus Z2 is less or equal to modulus Z1 plus Z2. And solution for the second part of the inequality in number 1, we have modulus Z1 minus Z2 is less or equal to modulus Z1 plus modulus minus Z2, and that is equal to modulus Z1 plus modulus Z2. For the first part of the inequality in 1, we have modulus Z1 is equal to modulus Z1 minus Z2 plus Z2, and this is less or equal to modulus Z1 minus Z2 plus modulus Z2. So, this gives modulus Z1 minus modulus Z2 is less or equal to modulus Z1 minus Z2, and this is number 1. Interchanging the role of Z1 and Z2 in number 1, we obtain modulus Z2 minus modulus Z1 is less or equal to modulus Z2 minus Z1 and equal to modulus Z1 minus Z2, and this is number 2. Combining these two, the result follows. Number 2, replacing Z2 by minus Z2 in number 1, we immediately obtain number 2. Inequality in number 2 implies that the length of one side of a triangle is greater than or equal to the difference of the other two sides. Another example, if the sum and product of two complex numbers are both real, then so that two numbers must be either real or conjugate. Suppose Z1 is x1 plus iy1 and Z2 is x2 plus iy2. Then Z1 plus Z2 is x1 plus x2 plus iy1 plus y2, and Z1 Z2 is x1 x2 minus y1 y2 plus I into x1 y2 plus x2 y1. By the hypothesis, we have y1 plus y2 equal to 0 and x1 y2 plus x2 y1 equal to 0. This gives y2 equal to minus y1 and x1 equal to x2, provided y1 is not 0, and hence the result. Another example, if fz equal to a0 zn plus a1 z to the power n minus 1 up to an is a polynomial in a complex variable z with real coefficients a0, a1, an, then we have to prove that conjugate of fz is equal to f of conjugate of z. So, since a0, a1, an are all real, we have conjugate of fz is equal to conjugate of a0 zn plus a1 z to the power n minus 1 plus an, and that is equal to conjugate of a0 z to the power n plus conjugate of a1 z to the power n minus 1 up to conjugate of an, and that is equal to a0 conjugate z to the power n plus a1 conjugate z to the power n minus 1 plus up to an, because a0, a1, an are real numbers. So, this we can write a0 conjugate of z bar to the power n plus a1 conjugate of z bar to the power n minus 1 plus up to an, and that is equal to f of conjugate of z. Last example of this module, find the upper bound of the function modulus z square plus 1 by z square plus z minus 6 when modulus of z is equal to 1. So, for mod z equal to 1, we have modulus z square plus 1 by z square plus z minus 6 is equal to modulus z square plus 1 by modulus z square plus z minus 6, and this is obviously equal to modulus z square plus 1 by modulus z plus 3 into z minus 2, and this is less or equal to mod z square plus 1 by mod z minus 3 modulus into modulus mod z minus 2, and that is equal to 2 by modulus minus 2 into modulus minus 1, and that is equal to 1. Hence, the upper bound of the given function is 1. So, in this module we study the definition of complex numbers, their algebraic operations, the geometrical representation of complex number, conjugate of complex number, polar form of a complex number, and how we can find the roots of a complex number. For further problem, you can see self assessment of this module and any reference books, and here we finish module 1 of chapter 1.